Your book discusses things like 8 exceptions. I am only requiring you to know 4. The reason I'm doing that is because in the past, when I've had them remember all of them, every transition metal they tried to do the exceptions to. That's not the case. So we're just going to look at these 4. I've grouped them in 2 pairs because essentially it's the same exception. So real quick, write out these 4 electron configurations. I'll do it also, but I can probably do it a little quicker than you. It would help if I had a periodic table. I didn't have to string my eye. Alright, so I've written the electron configurations. You'll notice, though, for these 2, the valence electrons look exactly the same. They're just in a higher energy level. So this is 4s2, 3d4. This is 5s2, 3d4. Okay? These 2 also look the same. They're 4s2, 3d9, 5s2, 4d9. Alright, so what happens is, for these 2, they take one of the s electrons, so it leaves me with 4s1. They put it in the 3d orbital, so that it's 3d5. The exact same thing happens here, it's just a higher energy level. So MO. That's 1, 4d5. All right, so if I would draw the orbital diagram for both of these, it would look like this. The reason they do this is because that this is super stable. It has one electron that's unpaired, so it's not being bothered by another electron in every available orbital that it has, okay? So in other words, it's completely half-filled. This is how these 2 elements exist naturally. And they do that because it's super stable. Okay? These two do something similar, but instead of completely half-filled, their d orbital becomes completely filled. So again, I take one of the s electrons, I move it to the d orbital. Now that d orbital is completely full. Transition metals kind of do whatever they want. You'll see that when we get to naming and forming compounds. They're always the exception to the exception. Alright, so with copper and silver, the stability comes from having that d orbital completely filled. So basically nobody else can bother it trying to bond with it because it doesn't have any room. So you just need to remember that these four elements, their electron configuration is what's drawn in blue, even though we would expect it to be what's drawn in black. Okay? And on your test, I would simply say, write the electron configuration for chromium. You just need to know that it's an exception. Okay? I wouldn't say anything about it. Yes, ma'am.
How does that change the shielding? Like I know earlier you talked about shielding the closest to the nucleus.
These guys have a lot of shielding anyway because they're in the D block and because of the way the D is oriented. So I really don't know. Again, your book mentions several others, but I don't want you to know those. I only want these four. Okay. Whew. Next thing. Ions. Should have placed my Wingstop order earlier. I really need to quit eating out. But I also hate going to the grocery store. Alright, what is an ion? Thank you. Okay, so it's when an element or a neutral atom gains or loses electrons. Remember, you never take away protons. So the only way you're going to make something positive or negative is by changing its electrons. Cations are positively charged. I remember that because cat have paws, so cats are positively charged. So they become positive by losing electrons. I haven't talked much about the setup of the periodic table, but most everything on the left side are what we consider metals, including the transition metals. Everything to the right, from like boron, it makes a staircase, I'll show you in a minute. Over, those are called nonmetals. And I'll spend a lot more time on that in chapter 4 because that's very important when it comes to naming. So, cations, positive charge, they do that by losing electrons and they're always metals. Okay? Anions, on the other hand, are negatively charged. Therefore, they're gaining electrons. These are always going to be nonmetals. All right, so we're going to talk about these in two categories. First, we're going to talk about our main group elements. If you look at the periodic table I gave you, it is divided for you, or there's kind of a bracket up top. Your S block and your P block are what are considered main group elements, transition metals, and your F block are not main group metals. So, main group elements follow specific rules, and they do this every time. Okay? Their goal in life is to gain or lose electrons to become like their nearest noble gas. Noble gases are that very last column, group 18 there. Okay? So, let's start with group 1. So your main group elements, you can predict or you can know what kind of cation or anion they're formed. They do that every time. All right, so group 1, it's going to be our first column here. We actually give this group a name. We call them the alkali metals. They always form a +1 cation. I'll show you one. Let's do potassium. All right, so if its goal is to be like a noble gas, the easiest way for potassium to become like a noble gas is just to lose that 1 electron that it has in this s orbital. That is much easier than gaining a bunch to become like krypton. Okay, so that's what potassium does. When potassium forms a cation, it forms a +1 cation, so its electron configuration is just that of argon, and that's literally all you have to write.
So you put the plus just because it loses one, so then you put...
Right. So if it's losing, it's always going to be positive. Gaining, it's a negative. Okay, group 2. We call these the alkaline earth metals. All of them in this group will form a +2 cation. So they're all going to lose 2 electrons. For an example, I'll do magnesium. Okay, so if I wrote the normal electron configuration for neutral magnesium, it's neon 3s2. Well, if magnesium forms an ion, it's going to form a +2 ion. So it's going to lose those 2 s electrons, and it becomes just like neon. Alright, the only other one, as far as cations go, is going to be aluminum. Aluminum is in the P block. In order for aluminum to become like the nearest noble gas, it needs to lose these 3 valence electrons in the third energy level. So when it does that, it looks like this. And it's just neon. So all of your cations will become like the preceding noble gas, so the noble gas right before them. Alright, so now let's switch and talk about anions. I'm going to start backwards. So the first group we're going to talk about, there's 2 different numbering systems for the periodic table. So you'll see sometimes it's called group 7A or group 17. The periodic table on the wall is 17. These are called the halogens, and they are all 1 step away from a noble gas. So if they can all gain an electron, they'll be like the noble gas that happens or that occurs right after them. So that's what they do. They gain 1 electron. So everything in this row gains 1 electron. So, for example, let me do neon real quick. I mean, not neon, chlorine. PS2. So chlorine neutral is neon 3s2 3p5. Well, chlorine prefers to gain 1 electron, so that's a -1 that I'm going to put on it to show that it has 1 extra electron. It's going to add 1 electron in that p orbital. So you could write it like this, or you could just say AR. Alright, if I move to the next group where oxygen, sulfur, selenium, etc. They're 2 places away from a noble gas, so they're going to gain 2 electrons to be like the noble gas right after them. Okay, so oxygen prefers to gain 2 electrons. I'll write it. 6A or 16 does not have a name. Oxygen's an example. Okay, so normal oxygen 1s2, 2s2, 2p4. If I gain 2 electrons, I'm going to put them in that p orbital. Or I could just say oxygen is now like neon. The last one that does this every time with no exceptions is nitrogen, and it forms a -3. Phosphorus and everything else in that column sometimes will, sometimes it doesn't. So you would need more information in order to predict what it was going to do. So just remember that nitrogen for sure will form a -3 because it's 3 places away from the noble gas. Put it up here. Nitrogen. It gains 3. Alright, one definition I want to add in here is the word isoelectronic. All that means is they have the same number of electrons, or you could say the same electron configuration. An example would be O2 minus, N3 minus, and neon. I know that because of what I just wrote out here. Okay, so when we start naming, you will have to know that these groups always form those type of ions. But if you think about why they're doing that, I think it's pretty self-explanatory. They're always trying to get to a noble gas. All right, now let's talk about transition metals. It's not much. All right, so I said a minute ago that metals always form cations. So transition metals always form cations because they are metal. Transition metals are not trying to be like a noble gas. Many of your transition metals, and that's actually why they're called transition metals, will form more than one kind or type of cation. Main thing you need to remember with transition metals, you always take away the s electrons before you take away d electrons. The reason is because your s electrons are lower in energy than your d electrons, so they're just easier to remove. Okay, so let's look at a quick example. Iron. I'm going to write its normal electron configuration real quick. Okay, So normal iron is argon 4s2 3d6. There are two common cations for iron. There's a 2+ and a 3+. All right, so the 2+, I take 2 electrons away. Well, remember, I take away the s electrons before I take away d. I'm only take away 2 electrons. Well, I have 2 s electrons, so I take both of them away. I have 4s0 3d6. I do recommend writing this to show that that you know what you just did. Okay, if I wanted to form the 3+, I'd go back to my regular electron configuration. I'm going to remove my 2 electrons first, but then I need to remove one more. So now I'll remove one of the d electrons. So it's argon 4s0 3d5. Okay. So that's all electron configuration. Only thing I have left in chapter 3 is the periodic trends, which is covered in part 5 of the lecture. Okay, so y'all be studying. Come see me if you need me.